Hello and welcome to this next part in this week's lectures on ETL patterns. We will continue from where we left off. We had looked at patterns related to loading data into the staging table in the previous part. So here we will start with an understanding of the next type of pattern, which is called as keys processing. Keys refers to a variety of different type of concepts which are fundamental to how data gets managed and gets processed as well. So first and foremost, you need to think in terms of what makes a data element uniquely identifiable. And that's where this concept of primary key comes into play. As the name suggests, it's a column in a table that has values which are unique and not null. And this is a foundational construct on top of which a variety of operations on data tables happens, including the C of CRUD that we took a look at in a week before, where the C stands for creation, right? So every time you do a creation of a new data element in a table, and usually these are what are called as dimension tables, then the primary key becomes the way to uniquely differentiate whether that particular data element has already been created, or if it's not been created before, then create it afresh and assign a unique ID or a unique value for that specific data element. A dimension table here refers to the fact that these are tables which are meaningful for the business in a way that is standalone and can be uniquely looked at as representing one facet of a business completely. As an example, let's take a look at the familiar world of IRCTC. The set of trains which have been in operation by the Indian Railways, you can think of that as a dimension table, because that's a set of data which makes sense in the context of operating the Indian Railways. And the primary key there could be the train ID or the train number. The train number is something we all know is a unique value. No two trains have the same train number, and you cannot have a train which doesn't have a train number, which means the train number cannot be null for a specific train. So in that sense, the train number for a set of trains table is the primary key for that particular table. So when you model data this way, using primary keys, it becomes easy not only to think in terms of creation of new data elements, but also in terms of how do you update data elements in place? How do you delete specific data elements? Because when you do these types of CRUD operations, you can use the primary key as the natural key on which you're doing a query. Like for instance, we want to know the number of tickets that are available in a specific train. As long as we know the train number, we can make a query which says, give me all the open seats available in that train with that train number equals a certain value. Likewise, I want to decommission a train, so I can say delete train where the train number equals a specific value. So that's the advantage of having a primary key in a particular table. Naturally, as you can imagine, a primary key construct helps you avoid having duplicate data entries, because the moment you create a duplicate entry, the train number in this case would have already been inserted before, and the database in which you're doing all of these operations that typically also supports these constraints that you have enforced, right? The primary key being a special construct or a concept, the uniqueness constraint will get violated the next time you try to write the same train into that same table. So that's the primary key. Let's take a look at some of the associated concepts as well. So a column in a table that refers to the entries in that dimension table using that dimension table's primary key is called as a foreign key. So if you look at a typical fact table, or in other words, an event table, it has the set of records of all the different transactions or events that have happened in that business. But by itself, it might not make much meaning because it needs to refer to a satellite of dimension tables, a variety of different types of dimension tables in order for it to have meaning. In this case of the IRCTC example, the movement of a particular train on a particular day is expressed as train number arriving at a particular station on that particular time and then departing from that station 10 minutes later. So in that description, the train number is used to refer to that particular train which has been recorded in the train dimension table. So the train number that's used in the arrivals and departures table is not generated by the arrivals and departures table. It's not generated by the station masters either, right? It's already been provided in a train dimension table, and I'm only referring to that particular train dimension table by using the same train number. So for the arrivals and departures table, the train number is not a primary key, but in fact it's a foreign key, meaning it's a key column, but it's a reference to a foreign entity. And in this case, this is the train dimension table where it refers to that dimension table's primary key. So that's the foreign key. Most databases again allow you to enforce this constraint, which means when you create these tables for the first time, you can specify that this particular column in this table is actually a foreign key dependent on the primary key of this other table. So when entries get made into this table, the foreign key relationship is checked and it's confirmed that the key that you're trying to reference here actually exists in the dimension table or not. So it's an enforceable constraint, just like primary key is. Now, in some cases, the business process could be structured in such a way that you do not have a clear candidate for a primary key, but you could have the ability to construct a primary key by looking at multiple different columns together. So let's take, in the next slide, we'll take a look at some examples in detail. When you have to do this, which means when you have to combine multiple columns in a table together to uniquely identify each row, and also, of course, not have any nulls in any of those rows or any of those columns, then that kind of a construct is called as a composite key. And last but not the least, there is a concept called as surrogate key. So here, the natural business process, which normally produces a primary key, a foreign key, and the columns that could be part of a composite key, are not able to uniquely identify a specific data element. If that happens, then you might need to artificially construct a column as part of an ETL pattern, as part of a database operation, which will allow you to create a primary key kind of a construct, but using mechanical means, right? It basically means that that particular key column, which is artificially constructed, do not have meaning in the real world, in the business process, but it's essential because it serves the constraint of being unique and being not null. When you do that, then that kind of a key column is what's called as a surrogate key column. So let's start with some examples to make this a point a little clearer. Excuse me. So first up, you have the users table, which is in the staging area rather. The users table has three different columns: user ID, username, and date of birth. And what I've shown you here in this is an extract from a CSV file, which denotes the data in that particular table. So you've got the user ID being 123442555. These are three user ID examples. The username, I've just picked hypothetically the presidents, some of the presidents of India, and their date of births. Please don't hold me to accurate data for this specific lecture. The point here is This is a typical way in which tables are modeled, where you've got a primary key for the users of your business. And in this business could be e-commerce, could be ICTC, etc. But the user ID becomes the primary key, is how typically the modeling happens for the customer data. And you model also two different salient aspects of the customer. So in this case, the name of the customer, the date of birth. Now, when new data sets are entered or when new precedents keep getting added to this table, as you can imagine, the primary key keeps getting added in a way that's unique. So that's the guarantee that the primary key of this table provides. So in this context, if you now look at what happens to the payment information. So let's take an example that these are users in an e-commerce platform and they are buying mobile phones as an example. And these mobile phones are of various types: Apple iPhone, Samsung Galaxy, Nokia E340, etc., etc. Variety of different products available. And the user dimension table is referenced in the payment fact table or payment transaction table. So that reference is manifested as a column called as user ID. It so happens that it's called user ID in the payment table. It could have been called UID. It could have been called something else. That doesn't matter what it's called. But the semantics is such that that column is modeled as a foreign key. By the way, these are data modeling decisions that the payment business process owner has taken when the payment system was set up for the specific business. So if it's for instance Flipkart, then Flipkart's data modeler for the payment processing engine has made these decisions already. As an OLAP developer, you do not really have much of a choice when you start dealing with data sets like this, because these have been decisions that have already been taken ahead of you taking a look at the data. So it is what you see that you have to work with. So in this case, we see that the user ID column, the name itself matches, but more importantly, there is a foreign key specification that's available in that database, which gives you the guarantee that that actually is a reference to the dimension table, which is a user's dimension table here. So that's one part of the system. Now let's come back to the users table. Notice that these are modeling real users of the system, right? So let's assume, let's explore certain scenarios. What happens when somebody in this users table ceases to be a user, right? Do you know whether the data modeler for the payment table or for the payment processing engine is not going to be reusing that particular user ID again at a later point in time? So a classic real world scenario is that many times customers ask to delete the account, right? They made their set of purchases and then they say that please, delete my account, don't remember anything about me. So in this case, let's assume Abdul Kalam did that, and Flipkart now needs to delete all references to this user. And this is especially, very relevant given the data privacy laws that are, very popular in many countries, including in India. So under that situation, this particular record pertaining to Abdul Kalam will get deleted. And when that happens, what happens to the user ID 123? Does it get retired or does it get reused? Now, if you've modeled this table with user ID as the primary key, you know for a fact that it cannot be reused again, because the deletion would not have removed the user ID. It would have just marked the user ID as deactivated or disabled. But because of the primary key constraint, you could not reallocate this specific user ID to somebody else and then add a row here. The table or the database itself would throw a constraint violation. But if you did not have a constraint set up there, or if the database is not set up to warn you of constraint violations. So then in which case the data modeler could have by mistake reused user IDs, which would have been the really wrong thing to do. And you would have had a really tough time when you start processing the data. So let's assume for now that user IDs are not rotated. They're not reused just because the customer has deleted their account. So that's the small discussion on primary key and foreign key. Now let's take a look at how composite key can be modeled here. Notice that user ID, name and date of birth are all available in this specific users table. For some reason, or for the reasons that we just discussed, like the customer deleting the data and the user IDs possibly getting reused because the customers have now deleted it. In those kinds of scenarios, the user ID column itself might not be sufficient. Then you might need to look at multiple columns together in order to ascertain whether that particular user is uniquely determined. So let's play with that scenario where the customer asks to delete their data. So Abdul Kalam has come in and said, Flipkart, please delete my data. So what Flipkart, the payment processing engine, might do is delete this entire row. So all references to 1, 2, 3 in this table are deleted, which means it's a hard delete on the back end. So the reference itself is removed completely. And whichever user comes in at a later point in time, the payment processing engine reuses that particular user ID. In this case, let's say it reuses 1, 2, 3, and it's a new precedent that's coming. Let's say in this new precedent's case, the same user ID 1, 2, 3 is given. Then 1, 2, 3, which is present in the payment table, right, is no longer sufficient as a foreign key reference, right? Because it could have been referring to Abdul Kalam back in the day when he was still an active customer, or it could be referring to the new precedent that I've added. At which point, the payment table itself, the payment fact table itself, cannot use user ID anymore. It now has to consider using a composite key, which is user ID, username, and date of birth. Why is that the case? Because user ID by itself is not sufficient to uniquely determine a customer. We can add the date of birth because obviously two users having the same date of birth and the same user ID is going to be a rare scenario. But a rare scenario does not mean it's a scenario that does not occur, right? A rare scenario does not mean it's guaranteed to be unique 100%, right? There is still a small chance that the same user IDs could be reused for two people having the same date of birth. And therefore, you might want to consider using username as well. So all three columns put together become the composite key. In fact, you could then ask the question, is it guaranteed 100% that user ID, username, date of birth in conjunction is going to be unique? There is still a possibility that it might not be unique, but that's part and parcel of your data modeling that you might have to take into account, right? And if even that is not sufficient, then you can always set up a surrogate key, right? By having artificially created user IDs, which are not part of the natural business process, because then you are enforcing that guarantee that the user is going to be unique. Okay, let's come back and look at the next set of concepts associated with it. Let's say that there is another part of the business which is called as registrations. So here, this pertains to customers of your business that have a loyalty to your business, and therefore they've signed up for the loyalty program. So they've registered for the loyalty program. Typically in companies, these are two different lines of businesses. The payment systems are separate from the registration systems or the loyalty systems, and usually developed by completely different sets of developers or teams of developers. So the registrations system is tracking its own set of users. Basically, these are users that have registered with my business for loyalty programs. And when they've done this specific data modeling, They have modeled the columns as ID referring to presumably the user ID, name presumably referring to username, and email associated with that customer as the salient columns which are part and parcel of every registration. So here the primary key for the users table, coincidentally it's also called the users table in that registration system. So that OLTP system, online transaction processing system, has the ID column in this table as the primary key. That's natural because its business process wants to track every single unique user that's registered for my loyalty program, and the name and the email address are populated. So that table has a set of primary keys, rather one primary key which has a set of values. Notice that the users table in the payment system is having its own primary key, which is user ID. The column names do not match, but that's not important. What is important, if you notice, is some of the user IDs are exactly the same. So 123 in the payment processing system refers to Abdul Kalam. 123 in the registration system refers to Margaret Thatcher. So I've just used, Prime Minister / Presidents of the UK as a counter example here. So now let's assume that you as an OLAP developer, you as a data management principal will have to now take into account a merging of these different data sets in order to answer interesting questions. Like one of the questions would be, give me the set of all users who are registered loyal users of my business who recently made a transaction on my system. So I want to know anybody who's bought a phone in the last 1 week, but who's also a registered loyal user. The way to think about answering this question is you merge both these data sets together. You pick up those users in the registrations table because those are necessarily your loyalty program registered customers. Do a lookup only for those users in the payment table. But can you blindly take the ID column here and look up the user ID that exists in the payment fact table? If you do, you might still get an answer, but that answer is very likely to be wrong. Why is that the case? Because 123 is referring to Margaret Thatcher, whereas 123 in the payment table is referring to a foreign key relationship to the users table in the payment system, which is Abdul Kalam. So you cannot just take the payment table and blindly join this with the users table and registrations. As a developer, you've got to take now extra steps, and that's where the surrogate key pattern comes into play. So let's dive deeper into this. What you do is you notice that these two users table are fundamentally referencing the same aspect of the business process, which is the notion of user of the business process, the customer of the business process. In one case, it's payment. The other case, it's registration for loyalty programs. So you take both of these users and integrate them and create a new integrated users table. And when you do that, that integrated users table has a bunch of information coming from the payment system, which is the payment users table, and a bunch of information coming from the payments, from the registrations table. But because you are an astute developer, you've gone through this course, you've sat through this lecture, you know that you cannot take user ID and blindly merge it with the ID column that's available in the registrations table. Instead, you create a brand new unique referencing key, which is called as a surrogate key. And that surrogate key gives a guarantee that in this integrated users table, this particular column is going to be unique and not null. So this becomes the primary key for this table, or also the referred to as a surrogate key for the table. Because this is now the unique key for this integrated users table, you also now can model each of the different occurrences of 1, 2, 3 separately, which means for the purposes of the integrated users table, all of the different columns coming from the payment system can be treated as naturally occurring business process related columns. So I modeled this directly. So user ID, which is available in my payment system, is modeled as it is. So that's 123442555. The user name and the date of birth coming from the same payment processing system is modeled as it is. Separately, I've got the user ID coming from the registrations table. So I've modeled that explicitly as user ID underscore registrations. That's 123442948, Margaret Thatcher, etc., emails, etc. And wherever the other system does not have data for a specific set of columns, I just mark them as null. So this is my new integrated users table, where for some of the tables, rather some of the entries, I've got data from one system. Some of the entries have got data from another system. In fact, in practice, you might have other entries here which has data from both systems, in which case you can gracefully model that. The table allows you the ability to model that without violating the uniqueness constraint, because that is enforced by the surrogate key. So I hope this is clear. So when you start doing your data pipelines, especially as a data scientist, you will find that a lot of time is spent in data preparation, and many of the data science courses do not really emphasize this aspect of data preparation. They focus more on things like feature engineering and things like that, model selection, not parameter tuning, and concepts which are related to the downstream aspects of data science. But the upstream aspects is, how do I merge and bring two data sets together? I want to create this nice, flattened data structure on which I can run my models. But even to create that, I need to have all of the different features, all of the different data points come together in a way that makes sense. I can't blindly merge data sets without paying attention to what those underlying data contexts mean, right? Okay, so that's the concept of keys processing. So we took a look at primary key, foreign key relationships back to the primary key, composite key, and surrogate key. Now let's look at one last associated pattern in this context, which is called as the reference key or reference data master data management. So this is actually a very lengthy topic. It can amount to a long discussion by itself, but we will touch upon the foundational aspects again and leave the rest of what typically constitutes master data management for a more advanced version at a later point in time. So notice that in that same example that we just took a look at previously, that there is another dimension that was available in the payment fact table, which is which product was actually being purchased: Apple iPhone, Samsung Galaxy, etc. How do you know that Apple iPhone or Samsung Galaxy are types of phones? Why can't it be types of refrigerators, right? I mean, it sounds so funny to ask this question, but for a machine to be able to reason about it without access to things like ChatGPT, you would typically need a master reference table. In most businesses, you will see these references floating around as Microsoft Excel files, right? For good or for bad, these are not tables in a structured database or a table in a structured system, but it's usually created by business team members using Microsoft Excel. Turns out to be still the most popular tool for them. And because it's Microsoft Excel, there is an enormous amount of variability that can be there. So let's deal with the simpler versions, simpler variations that are possible. And then, like I said, the more advanced variations of how Excel can be used and abused for these kinds of data management will be potentially addressed in an advanced version of this course. So if you take a look at this simple Excel file, I'm just going to assume there are two values, one for iPhone, one for Galaxy. Notice the way I've represented it as well, right? Apple iPhone, Samsung Galaxy. They belong to this category called smartphone. I go back to that payment table I was using as an example. So 123, which was Abdul Kalam, bought an Apple iPhone. So the Apple iPhone word itself is there for a specific amount at a specific time. Now, notice that the payment table is referencing a phone which is called as Nokia E340. So what happens when you start processing this payment information? because there is a product that it references which does not exist in this Excel file, right? So the Nokia E340 is actually missing here in this Excel file. Now you could ask this question of how could it be possible that the payment table is registering it, but the Excel file does not have it? So it comes down to, again, the modeling assumptions that are made. The data modeler for the payment processing engine might have encoded a lot of data modeling decisions in the underlying table itself, like we saw with foreign key, primary keys, etc. But because he or she is a developer, they are not the ones calling the shots on what products are available to sell. That's a business team member's decision, right? And that business team member does not use databases. They use Microsoft Excel. So they use a completely different tool format in which they collect and process data. So when that happens, typically that is creating a completely different version of truth. And here the truth refers to the set of products I as a business have available for me to sell. And that separate data is fed to the payment system in an offline manner, meaning the business person operates on this Excel file in a laptop like this or a desktop like this, and separately gives it to the developer and say, hey, this is the set of products available to sell. Whereas the developer has modeled all of the other tables that he's working with on a database. So when that happens, naturally there could be differences in the version of the truth, right? Business thinks that we are selling only 2 phones, but the website is actually having 3 phones, access to 3 phones. That could be one reason. The other reason could be that the payment systems, the data sets for this are available to you as a developer in real time, meaning that these are automated systems, machines talking to machines. So when the OLTP system makes a record of a specific transaction, immediately that data is available to you as an OLAP developer. But the Excel file from the business needs to be sent by a human, right? The business team member needs to send to you the data. And when that happens, they might not be sending it to you on an automated schedule. They might send it once a week, once a month, once a quarter, because products do not change that frequently. And when that happens, for a period of time, the backend system of the OLTP is already updated to use all the latest inventory of products available. So it's recorded that Nokia has been sold, but the business team member has not given that data to you. By the way, this is very common in the world of data management, right? In real world, you will find that all the different ways in which data can be produced, each way has its own frequency for refresh. So when that happens, naturally you're going to have a difference between one version of the truth and the other version of the truth. So what can you do for these kinds of situations? One way to do data processing on this payment table now is to continue to treat this particular set of data for which the products are available with you, which is Apple iPhone and Samsung Galaxy, but reject any product that you don't understand or any product that you don't have in your mapping file. If you do that, that's a theoretically okay way to solve this problem, but it's the wrong thing to do intuitively, right? Because it doesn't serve the business purpose of recording every single payment transaction, right? You've destructed this particular data. You've intentionally, deleted this specific data for consideration. A better way to handle this particular way of, having missing data in the reference table is you make an entry in your reference table that, hey, I noticed this specific product. It wasn't there when you gave me this reference file as an Excel, but I've made an entry because I found it in the payment table. Now you can go back to the business and say, look, here are all the products which have been recorded in the system, which I have captured, which you have not provided to me. Now you tell me whether these products are legitimately being sold, or is that a problem in the supply chain? Is that a problem in the inventory management? So that's a better way to solve it. So if you go down that road, which is the more practical way of handling this specific data problem, you essentially, introduce a concept called as a reference key. That reference key, as the name suggests, is a unique ID. That unique ID is created by you as an OLAP developer. And when you do that, every single product and its version will get assigned a unique key. So the reference key becomes the primary key for that particular reference data. And any specific reference to that product name in the main event table will get replaced by the reference key. So I'll create a reference table, and in that reference table I'll create keys which are the primary key for that particular product names. So Apple iPhone will have a key, let's say 1, Samsung Galaxy will have 2, etc. And so when the payment table gets processed, user ID 123 bought Apple iPhone, which means user ID 123 bought key 1, right? Reference key 1. 442 bought reference key 2, which is Samsung Galaxy. So when I come to Nokia E340, I give it a reference key of 1000 as an example. And I make an entry into my reference table that says reference key 1000 refers to Nokia E340. I don't know what that category is because nobody's told me about it yet. So the category column will be null. But by introducing this abstraction of a reference key, you can make progress with processing this particular type of data. Notice that there is actually one more problem here in the way that the example is showing the product name. All of us in the real world know that there is no single product that's called as Apple iPhone, right? There is, iPhone 13, iPhone 14, iPhone 15, etc. So the words 13, 14, 15 are also part and parcel of the product name to uniquely identify the product. Until then, it just becomes a brand, right? Apple iPhone is just a brand. So when the payment table tells me that 123 user bought Apple iPhone, which version of iPhone is this? Is it 13, 14, 15? So that also is a manifestation of the same problem, which is my mapping file, is my master data file clean enough for me to use directly as a lookup for the payment table? If not, you have to go through your own reference data management process, right? Where you introduce the key, where you manage the different versions of the product, etc., etc. So with that, we've concluded this specific part of the lecture. In the next, we will look at other salient ETL patterns.